What's up, Eigen folks? Welcome back, guys. Make sure you like, share, comment, subscribe, all that nice stuff. Make sure you check out the website, Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then thank you, patrons. We greatly appreciate you guys supporting the channel. If you guys want to sign up for our Patreon, it's patreon.com/Eigenbros. Me and Juan do a 30-minute audio podcast there every week. So you can check that out. You know, you guys just donate $1. That's all we ask to help this channel keep running. And let's just jump in, Juan.
Yeah, let's jump in. I feel like there's something missing.
Is there? I kind of blew through that intro.
No, it's good. It's good. We also have a Discord.
Oh, yeah. Discord.
And you can reach
with
us
the
at
Patreon.
the Discord. Yeah, with the Patreon.
So check that out.
Yeah, check that out. But anyway, let's talk about some freaking time crystals, man.
Yeah, boy.
Some freaking time crystals.
Time
dude.
crystals. So, yeah, the name already kind of makes you not want to research it.
Yeah, I had the same thing. It's a very wooey word, isn't it? Yeah.
So, this was one that I was kind of reluctant to look at.
Yeah.
Although I knew it was legit because, Lex Friedman did a podcast with Frank Wilczek talking about it, and that's the guy who basically invented the concept.
First of all, what are crystals?
Yeah.
And what time crystals?
Okay, so crystals are orderly arrangements of atoms in space, and time crystals are the same thing in time. Basically, but of course it's not. So it's not positions of atoms, but it's orderly behavior that certain states of matter will arrange themselves into spontaneously if you do them, if you treat them gently and let them do what they want to do.
But of course, some of these things you got to be reluctant to research. Me and Juan got a lot of shit to research typically, so we've got topics all day to try to look at, and you've got to use your time wisely. But then of course we came out with the news came out recently with Google. They used the Sycamore processor, which is one of Google's quantum computers, to actually make a time crystal. So that's when I knew, and you knew as well, Juan. It was like, yeah, this is something we need to actually definitely look into.
Yeah.
So so shall we talk about it then?
Yeah, because I mean, the quick synopsis, like if you're like, what the hell are time crystals? They are objects that undergo spontaneous periodic motion in a system's lowest energy state. Is that probably the best way to put it?
Pretty damn accurate. If you want to dumb it down even further,
sure,
just think of it as wiggling crystals.
Well, wiggling, collection of like, and what we mean by that is, I think the most rudimentary or simple example is like an arrangement of quantum particles, like qubits or something. Yeah. Arranged in a sort of lattice.
Sure.
And
okay, you're trying to go into it now.
Yeah, okay, just so you can, just to kind of give you a picture, like crystal is a loaded term. It's like when you think crystals, you think like Terrence was saying, valley girls with, or maybe like, hippy dippy dudes would be like, yeah, dude, spiritual, man, time crystals, man, it's going to take you back in time.
Aligning chakras and whatnot.
Yeah. Aligning chakras and, believe it or not, time crystals are not going to take you back in time, or they don't have anything to do with time travel or whatever, as much as you would think that it's like going to unlock something. And
right.
Yeah.
But it was interesting because a time crystal basically was invented by Frank Wilczek, all from, it spurned from the idea of space-time, basically. So, those of you may be familiar with Einstein's work on relativity, space and time has this kind of relationship. Einstein discovered that, after he just basically took the axiom that, oh, maybe the speed of light is constant. Because, experimentally, people were finding that the speed of light was constant in all these reference frames, no matter where you were moving. Some of you may have heard the Einstein train analogy where he's on the train and the lightning strike happens. And it's trying to go through that scenario to show you the different ways that relativity maps out this, how space and time work with this analogy. And what was my point?
I wonder what he was doing on that train. Like, I wonder if he was like having tea or something, like, and he's just like, I don't know, like Gegenheim or whatever. I don't know what you said. German? What is that, a German word?
Probably.
What's a good German phrase? Some German phrase, and then lightning stroke. He's like, "What's the hell?" And then he's like, "Oh, Eureka," or something.
Great story, Juan.
I just want to know what he was thinking, because unless he's one of these guys that are very romantic, and like looks outside the window and is like contemplating life.
I think that's more Einstein style.
It's more Einstein style.
Yeah.
All right.
He's a contemplator, full stop.
Yeah.
So I don't think lightning struck his train at both ends.
Okay. Gotcha. I just imagine him being like kind of emo, looking outside the window, and just yeah. So that's what you're saying, like to paint a picture.
He's the god of the thought experiment.
Yeah.
So I mean, you gotta assume Einstein was
staring at the window, being sad. No one gets me with the universe. And
Right.
so he saw the lightning strike, and then I guess I've heard a different story. That's why.
Maybe, I don't know.
You know, people love to make these embellishments and things after the fact.
Yeah.
Anyway,
yeah. So yeah, his idea that space and time are intricately linked. So this guy.
So he just thought of a concept of like, okay, we know these crystals have this spatial symmetry, right?
Mm-hmm.
I think they call it like a discrete. It's a spontaneous symmetry breaking in space. And of course, I can already see the eye rolls of what the hell is spontaneous symmetry breaking, and that's kind of the same eye roll I had, because I was like, damn it, now I got to look up spontaneous symmetry breaking. And spontaneous symmetry breaking is one of these concepts that comes from quantum field theory and many-body physics. So many-body physics is kind of the condensed matter version of quantum field theory in some sense. Mm-hmm. You learn many of the same concepts like renormalization and things, and of course, like we mentioned, spontaneous symmetry breaking. And you might have seen pictures, like if you type in spontaneous symmetry breaking in Google, you'll get the classic sombrero shape that shows the graph of, you've got this ball sitting on an unstable position, and then there's some kind of perturbation that causes that ball to fall into a new ground state energy. And the ground state can be several different ground states, and then it's locked into this asymmetrical state or something.
Yeah, and the reason why is because, like, I mean, you're comparing the system in its high symmetry state, versus
in its unstable equilibrium state.
Yeah, in its unstable equilibrium state. Yeah, sure, there's more symmetry. Like if you're on a sombrero right in the middle, right?
Yeah.
But then, like, the particle's going to choose the lowest energy state.
Right, because it takes a very small perturbation to make it collapse into its more stable but less symmetrical
state,
ground state or whatever.
Yeah, and the sombrero is a good example of that.
Right.
Yeah, and that's
kind of looks like one of those air hockey pucks.
True,
or one of those air hockey paddles, I guess you call
That's
it.
a great example, yeah. I always thought the sombrero one was a little bit like insensitive to people who like sombreros.
I thought you were saying sensitive to Hispanic people.
Well, yeah,
but you're speaking from a cultural...
that too. I mean, I always see the literature papers literally say Mexican hat.
Oh, yeah, yeah.
And I'm like, Mexican hat? You can't think of anything else? Something more appropriate?
Well, it does look like a sombrero, to be fair.
It does. I mean, I'm not going to knock them on it.
And who cares? I mean, what are you hating on sombreros?
Kind of, yeah. No, I'm just kidding. No, I just think Mexican hat, there just could be a hockey. The hockey one is a better way to put it, I think.
Okay. The hockey paddle.
Air
hockey paddle.
That's more relevant. When was the last time you saw somebody with a sombrero? You know what I'm saying?
I've definitely played more air hockey than worn sombreros.
That's what I'm saying. Like, I'm just like, because I'm like, a sombrero? Why would a sombrero? But then the air hockey thing, it's like, oh yeah, imagine if you have a little ball on it, and you push it either way, it's going to reach
right
either side. It's going to be on the side.
Or you can even say, like, the air hockey puck hits the paddle, and then that causes it to fall into the...
Yeah, there you go.
I don't know.
Yeah, this is a better analogy.
Anyway, cultural insensitivity inside. It's just that's an abstract representation or an abstract graph, a graphical representation of what an unstable equilibrium state looks like, where you fall into a more stable ground state equilibrium.
But it's not symmetric. Yeah.
Right.
Yeah.
That's the key. The spontaneous symmetry breaking occurs once that new ground state's achieved. And you might be wondering, like, how's that? It's because, one of those sombrero sides is now, if you imagine that graph is cut in half at the midpoint, now you're on one side or the other of the graph. Whereas if you were on that unstable equilibrium position, you're right in the center, and it has more symmetry, more rotational symmetry.
Yeah.
You know, if you rotate the other one where it's already in its ground state now, the unstable or the less symmetric equilibrium, when you rotate that, you have to rotate it a full 360 degrees to be back where you started. So there's less symmetry there.
Yeah.
So this is what a time crystal basically is. It's one of these objects where you actually have a less symmetric ground state. And that's because, you know, your ground state now with these time crystals is oscillating in time. So if you imagine like the crystal structure, the lattice structure, as one was saying earlier, with like a qubit array, you can think of all these different qubits in a line, and they can have, you know, let's say a spin up or a spin down, which you may be familiar with as kind of the magnetic moment of an electron. So you can just think of an electron literally as a tiny bar magnet. So an array of these tiny little bar magnets, which are electrons, or just some kind of atom, you know, these things can oscillate up and down when they have some kind of laser directed onto them. And then that's an example of the time crystal. So once they have that laser shown on them, they start oscillating in time, and they do this indefinitely. So it's a pretty crazy concept, and you're almost like, how the hell is this even possible? You know, like you have lasers hitting this lattice structure, and then it's oscillating indefinitely. Like, what the hell? Like, how's that real? It sounds like even Frank Wilczek mentions this in his original publication on it. Like, it sounds like a perpetual motion machine. Right?
It does, yeah.
And then, you know, of course, in physics, and I think even Lex Friedman mentions it on his podcast, you're like, you know, perpetual motion is not something that, this is one of these things we know in physics is just not going to be true, right? Because when you have something that has energy, when you're dissipating energy,
no, when you're doing work, when something's doing work,
right, which is dissipating energy, that means you're eventually going to get to zero energy,
Yeah.
right? It doesn't make sense to have a perpetual motion machine. But that's the key here, is the fact that this guy is not actually a perpetual motion machine, because this weird oscillating equilibrium state is actually not dissipating energy. So it's just
the ground state.
because it's the ground state, exactly. So the ground state energy is the lowest energy configuration. And even when you think of the laser, you might say, okay, there's a laser being shown onto this lattice. You know, there's some kind of laser which acts as like a kind of like a applied field. So if you know lasers, they have, if you see the classic picture of a laser, we've got that oscillating sinusoid, you know, of the magnetic field, and then the electric field that's perpendicular to it. When you have that oscillating B field, which is a magnetic field, directed on these little tiny bar magnet electrons, then those electrons want to oscillate with that field. They want to align with that magnetic field or not. So then when it happens, you're like, okay, there could be some energy being dissipated to this lattice through the laser. But that's actually not the case. The laser is just acting as the oscillator, essentially. So it's tuned to some frequency, and then that frequency just oscillates that time crystal, so it keeps going. So it's actually not adding any energy to the system. So this truly is like the ground state of the system.
Yeah, fascinating.
Yeah, weird
stuff. Yeah, the beauty of it is that, like, we've been wondering for a long time how you can make, like, especially in quantum systems, how you can have something that stays coherently in the phase of in this quantum system, right?
Can you say that one more time?
Because in this quantum system, like for the qubit arrays,
Yeah.
the qubit lattice that you're thinking about,
Yeah.
creating this time crystal,
The Google kind of quantum computer version.
yeah, it's allowing for a stable quantum state that isn't going to be destroyed.
Right, that's the
Yeah.
reason why they were so interested in it, right?
Yeah.
Because like the decoherence problem is one of these huge problems that all these quantum computing groups are trying to figure out, right? And decoherence is just like, you have to be able to maintain that information state. So if you have a qubit, right, when we want qubits to be in superposition in quantum computing, because that allows you to do those really crazy, you know, Grover's algorithm, Shor's algorithm computations, is using that superposition, which is, you know, the combination of the 0 and 1 state of the qubit. So they're trying to figure out these ways to get around decoherence. So people are thinking that these time crystals might actually have application in somehow getting past this decoherence problem. at least the research that I saw, I didn't see much about superposition, so I can't really say how that
Well, it's still in the
works.
superposition of states, but the picture that I have is that you have the allowed set of states that it's in, given the Hamiltonian.
Yeah.
Like, because you have the wave function of your particles, right? Of
Okay.
your system of particles, right?
Yeah.
And it's still in superposition, but you know that you don't know the exact, like, I don't think you know the exact spin state configurations, but because they're oscillating.
Yeah, but if they're in superposition, it's more clear to me when you're just analyzing it where it's already just spin up or spin down particles in some lattice. But apparently that is something that they're looking at in order to increase the coherence time of those qubit particles. So this is why it's so relevant and why it's such an interesting field right now. It's the first phase of matter that has this weird persistent equilibrium state.
Yeah.
Although it did immediately come to mind. So I was reading another paper, but I think it was Christoph Sasha, I believe it is the name. You can check that out on Google Scholar. I think it's like a 2017 paper. It's called like the quantum or the discrete time crystal review or something along those lines. It's probably the wrong name, but you can find it.
I'll find it.
Christoph Sasha.
It's a review paper series, right?
Yeah, I believe. I think actually I read so much though I don't remember if this is the right one, but
Okay,
I think that they mentioned a superconductor with this. And as you know, superconductors have a persistent current, right? You can create this persistent current in superconductors. And that's because superconductors have the zero resistance state. So once you hit a certain temperature, let's say if you go down to like some critical temperature is what we call it in condensed matter, you get this weird state of matter where now you have these Cooper pairs and you have zero resistance within the material. And then you can have current that actually lasts forever. So, or in theory, it lasts forever. It's a persistent current. So now I was like, oh, this is another example of one of these weird equilibrium phase states where you could have something that persists without losing energy in this equilibrium state. And then I was like, oh, and it happens to be a superconductor. And then what are the type of qubits that they use in quantum computing a lot of times?
Superconducting qubits.
Superconducting qubits. So I was like, there has to be some kind of relation here, I would imagine. And Christoph Sasha did mention in that paper, so I think there is. I didn't get to read it fully, though. But I imagine there is some kind of link. So these are all just, I guess, little clues to linking how this could be related to quantum computing. I wish I could elucidate more. Of course, I didn't get enough time to research it fully, but these are just some things that you can check out yourself and can, I guess, kind of give you ideas of what the direction for time crystals actually is here. And it seems like there is some really strong, or at least there is some linkage between quantum computing and this.
Yeah, I kind of wanted to give a more physical picture, a better picture of like what Google's doing.
Yeah, sure.
It says here Google's qubits, and this is from Quantum Magazine. I'll go ahead and link the paper, but
Yeah.
Google's qubits consists of superconducting aluminum strips. Each has two possible energy states, which can be programmed to represent spins pointing up or down. For the demonstration they did, they used a chip with 20 qubits to serve as the time crystal in their example. Like we were saying, the sort of qubits in a lattice kind of thing. They said perhaps the main advantage of the machine over its competitors is its ability to tune the strengths of interactions between its qubits. This tunability is key to why the system could become a time crystal. The programmers could randomize the qubits' interaction strengths, and this randomness created destructive interference between them that allowed the row of spins to achieve many-body localization. So you basically confined the qubits in this many-body localization picture.
What is a many-body localization?
There's a little picture that I'm going to put up here, but you can think about it as a row of particles, so each having a spin. Imagine that. This is a way to illustrate it here. They typically settle into an arrangement with the lowest possible energy, but random interference can make the particles get stuck in a higher energy configuration, and that's what they call many-body localization. The best way to put this is you take a single particle, right? So in a solid or in a lattice, like an electron can become electric, what is it called? It's called Anderson localization or something. It's a physical phenomena where you basically have confinement of this particle within the structure of this crystal, or with this physical object that you have.
Okay.
So in essence, that's kind of what they're doing here, but with many particles. The particles are being confined, and you get a destructive interference such that your particle is basically localized to a certain point. So
Editor's note: localization should not be confused with quantum confinement, as localization effects occur from wave function interactions that either occur destructively or constructively. Quantum confinement is a phenomenon due to the applied potential or the physical constraints of the experiment that the particle is in.
It's interference from what?
From the lattice, usually, but it can be from other. It can be from other neighboring particles as well. So localization effects take place for quantum particles when they become confined by interference from other particles. Hence, many body localization.
1 hour later.
Like, wouldn't you agree that
Sure.
in the ground state you still have superposition?
You
Or
like
no?
you can,
Yeah.
but it just doesn't make sense in the context of this time crystal, right? Because the thing is, for the time crystal to work, it seems to me, is you need to have these spin up, spin down states already kind of set, and they're constantly being hit by this laser anyway, because it's in a field, right? And I'm pretty sure if you have a magnetic field on a particle, you're already breaking that superposition.
Oh, this is okay. This is where we're getting mixed up.
Okay.
Because you're picturing the laser example. I'm just picturing an array of. So this is
Well,
the
then
example.
what tunes the frequency though?
What do you mean?
Because something has to tune this frequency, right? In the Max Planck Institute version with the magnons, let's say, there's another version of this experiment with time crystals with magnons, which are spin waves. This is kind of both of our area of research, spintronics.
I never did spintronics, but sure.
But wouldn't you consider
worked
yourself
with
spintronic?
spin.
Yeah,
I was hoping to.
Okay. Well, I did spintronics in my undergraduate, and
Yeah.
I was in a spintronics group, but I didn't really do that much spintronics with it. But that has to do with spin waves, and they're like excitations, these quasi particles in a lattice, which are called magnons. And there's an example that they do of the first video ever of a time crystal where they use magnons, which are these excitations in the lattice, basically. And what was my point? Oh, they were tuning that time crystal with the magnons. And then in the other example, I think with maybe the I forget, with the spin ring or with the time crystal ring or something with Christopher Monroe's group, I think they might have used the laser.
Yeah, the particle rings.
But there has to be some driving frequency in order to make this
exactly
work. So
Yeah.
in this example, what are they using?
Well, in this example, they're just talking about how it's happened spontaneously, with like certain physical effects, like how a particle is even localized to begin with, or how it can be localized to begin with,
I'm lost.
to achieve a ground state configuration that breaks spatial symmetry. You can have this exotic state where the particles are localized, and but that's kind of where the idea of like crystals comes in, because they sort of form this weird solid mixture. And in physics, they don't call them time crystals in condensed matter. They call them spin glass, I think, typically.
Yeah, the first paper I think that was written on it was called a spin glass or something,
Yeah.
and then they only recently added as an addendum to the paper calling them time crystals.
They're
I
like,
believe.
technically it's a
Technically, it is known as a pi spin glass system, with pi being referenced to 180 degrees. It also sometimes referred to as floquent time systems, as mentioned in the following lecture by Kurt von Kieserling at the University of Birmingham in the UK.
Asked me today to give just a pedagogical overview of the simplest example of time crystal, and other people call it pi spin glass, other people call it discrete time crystal. My lab's been calling it pi spin glass.
It's a time crystal.
Yeah.
But spin glass is probably the best way to put it. And I think it's more a more physical picture, because the theoretical paper is a little bit, it's kind
Hard
of
to
all over the
understand.
place. Yeah. And I kind of wanted to go through it because I wanted to see the original content and like
Sure.
dissect it a little bit and see what the motivations are and see how they tie into.
Sounds like a landmine for a podcast, but let's do it.
We'll just kind of debate what it is, because we answered what are time crystals, right, through our own little research here.
Yeah.
And this paper came out
Well,
in
kind of. One other thing we should actually probably address is the
Sure.
thermodynamic part of it too.
Oh, we'll get to it. Yeah.
Okay,
Yeah.
sure.
We'll say that to the end, because
Okay.
that's a good way to like use this as a launching pad here.
Okay.
But I kind of wanted to go back to what I meant by the definition of time crystals, like where, you know, the object, or this physical object, or this state of matter almost undergoes spontaneous periodic motion in the lowest energy state, or the ground state.
Yeah.
Like you were saying, the object doesn't require any energy to keep it in motion, or be in to just be in a state of motion, right?
Yeah. It's this weird phase of matter that we just discovered, the first of its kind, I would say, where it's got this persistent quality, where it can continue on in this state indefinitely of this time, this oscillation in time of these spin moments of the atoms.
I like spin glass better than I like time crystals.
Me too. But the thing is, time crystal does sell better. I think it's a better marketing term for
journalists are probably eating that one up because they can, you know, it's just so easy to sell that, right?
To get clicks, yeah. And best believe we're going to put time crystal in this.
Yeah, of course.
This will be the one that gets more hits. Spin glass gets like 20 hits.
Yeah.
Time crystal gets several hundred at least.
Yeah. Well, the author addresses this in his first paper. He collaborated with a professor from University of Kentucky, or Kansas. I'll have to fact check that.
Okay.
But him and Frank, they worked on this paper, sort of classical time crystal, and this was in 2012. And they stated, reasons for doubt appear. Speaking broadly, what we're looking for in our solution seems perilously close to perpetual motion. You know what I mean?
Right.
And he's right. I mean, there's like everybody side-eyeing this, like, okay, guy, like,
like, come on, bruh.
Yeah. And I mean, they talk a lot about like sort of these symmetry concepts, like time symmetry and spatial symmetry. Yeah,
this is one that kind of helped me elucidate a little bit more on time translational symmetry in these things. I mean, I'm still a little bit. This has helped me get a little bit more comfortable. It's the terms on this are really kind of thrown about in a confusing way.
Yeah,
like they'll talk about spatial symmetry and time symmetry in this a lot on the time crystals, but it's very confusing. One thing I've noticed that they've mentioned is, you know, the whole fact of a crystal, an interesting property of crystals is that they have this continuous translational symmetry is what they call it. And from what I'm seeing is that just means you can move the particles anywhere in space and you retain the symmetry. But then there's this weird symmetry breaking. Sure.
Yeah, because that's not immediately obvious to people.
Not to me. I still don't really know if I believe what I'm saying.
Because like in condensed matter, you know, we have like the physical solid crystals that we have. There are maybe only 14 types of lattices. I think the Bravais lattices. Remember this?
Yeah, I think so. Yeah. For the spatially periodic ones, because there can be amorphous solids too, right? Which are glasses.
Yeah. But in the sort of highly symmetric crystal lattices, you know, we have 14 types, which is kind of insane to think about.
Yeah.
Well, we've only discovered 14 types, and we think there are only 14 types of lattices.
There's weird things like metamaterials and quasi-crystals and things out there. Yeah. But yeah, there's like the common ones are like the body-centered, face-centered, cubic, these kind of structures, zinc blende. These are like the kind of prototypical crystal structures you can think of.
Yeah, and we pick this. Oh, we say that because essentially what happens is you constrain the lattice to its most basic structure, meaning that like it serves as a motif. Like once you have the basic periodic structure of the lattice, then you just copy paste, translate it spatially, and you have high symmetry. You know,
right? And condensed matter people or crystallographers like to call it the unit cell.
Yeah.
It's like the smallest cell in which you can just copy and paste and create the whole crystalline structure.
Yeah.
As Juan was saying.
Yeah. No, it's a good point. Yeah, but that's where we get our acutely our sense of like spatial symmetry in this picture of crystals. But time symmetry was something I'm like, what the hell?
Yeah, you're like, how does that even make sense in the context of a crystal? And then the crystal name throws you off because really the time crystal, the crystal in that name is not actually referencing the spatial crystal structure. Because you're like, what the hell? The crystal in it is actually using the more abstract term of the word crystal. So crystal really just means something that has this kind of discrete periodicity to it. And they're saying that this time crystal, although it happens to maybe be a crystal sometimes, not always, has this time symmetric component because it has this periodicity in time of this object. So that's really what it's saying. It's got this symmetrical property to it that has this discretized symmetry. And the symmetry breaking comes from the fact that I believe, I'm not even entirely sure of this, I think that they're saying it has this symmetry breaking aspect is because it goes from a continuous symmetry to a discretized symmetry.
Exactly, yeah.
So it's like there's
a transition there.
Yeah, there's a less symmetrical state in the ground state than the original state. The original has a continuous one, which you can think of in terms of like integration has this continuous property, right? When we integrate something, you have this concept of the differential, and you're integrating something in a more analog or continuous fashion. And then there's the discretized version, which we can think of in terms of like systems that have like quantum mechanics, or like systems that like natural numbers are discretized numbers in some sense. Like the actual real number line is contains every number possible, but then you have these natural numbers which have these discretized whole number units. So the discretized version, or discrete time crystals, are basically this object that has this lesser form of symmetry in its ground state than comparative to its original state, whatever the original Hamiltonian says about the state.
Yeah, and
I think I use a lot of jargon there,
no, sure,
I really
but
hope people can understand what I was saying there.
Yeah, I kind of want to fill in the gaps because I think your description there is pretty analytical, but for people who like want to have a more physical picture, I like to use the example of like, especially with spatial symmetry, it's like easy to capture, like, okay, a ball in space, right? It looks, and any way you rotate it, it's going to look the same. Right.
It's got a huge number of symmetries, right? Because a sphere, you can rotate it almost anywhere.
Yeah.
And it looks the same everywhere, as long as there's no distinctive markings on it, like in a plane sphere, boom. It's infinite symmetry, really, I believe, right?
Yeah.
Because you can rotate it at any degree measurement. It's the same.
Yeah. But in time symmetry, you could take that same sphere and press record on your camera and watch the ball roll or something and play it backwards. The events are going to look the same forwards and backwards. It's not going to be like it's a continuum.
Right.
The thing that breaks time symmetry would be an event like the ball is rolling and then all of a sudden like it clips or something.
We're really talking about, in this case specifically, it's more so of
breaking
the discrete time symmetry.
Yeah.
So if the ball was, I don't know,
like I was saying, like remember VHS whenever like you would skip in the movie?
Right.
That's kind of what I'm thinking. Like you're like, okay, it's continuous up until like, well, how did I get to this point?
I see. So you're skipping a few frames. You clipped some of the film out.
And that's kind of what we mean. Like you remove that context and you see the object somewhere else where there's no continuum. Like it's like the integral analogy that you gave.
Yeah.
It's like
I don't know if that's a perfect analogy, but there's something to it there.
Yeah.
I wish we could think of more of a system that has discretized time units or something somehow.
But essentially the particle or this ball that you're rolling doesn't look the same when you run the tape backwards. There's an event that happens in time when things
I don't even know if that's true, because it's like the time crystal looks the same forward and backwards. Because if we imagine the video of the time crystal, you can run it forwards and backwards, you won't be able to tell. It's the discretized part which makes it a lower form of symmetry than its original Hamiltonian.
Right, but I'm thinking about time symmetry breaking. Events. Yeah, I'm trying to.
That's a little bit different. That's a little bit separate from the concept of the time crystal, because I don't think it's breaking time symmetry. It's just a discretized version.
Yeah. I'm trying.
But there are things that can break time symmetry.
Yeah, but I'm saying I'm trying to like define these terms a little bit, because you're going to see them a lot when you're reading like this stuff, and you're going to hear
this
that a lot.
This has given me a nice little crash course on symmetries, which I neglected throughout grad school. I don't know how.
They didn't really.
I guess we didn't really need symmetries that much at the time.
They don't emphasize it at all.
Yeah.
But because I want to go back to the paper, how he made classical time crystals, or making the case. And so an excerpt here I want to give. They're saying when a physical solution of a set of equations displays less symmetry than the equations themselves, we say symmetry is spontaneously broken by that solution.
Right. So the key is less symmetry.
Yeah.
This is what confused me for the long time, because when you hear spontaneous symmetry breaking, you think, oh, now it's anti-symmetric, or now it's not symmetric at all.
Yeah.
Right? And it's not the fact that it's not symmetric, it's less symmetric is the key.
Yeah. And he's saying here the meaning of physical solution is of the lowest energy solutions of a time-independent conservative classical dynamical system in this case that he's giving. If such a solution exhibits motion, we will have broken time translation symmetry spontaneously. If the dynamical variable is an angular variable, blah, 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 then the motion will be periodic. So, but that has to do more with like our physical intuition as physicists. Like something is angular, it's going to be periodic, blah, blah, blah.
Right.
Anyway, like dissecting that, I kind of wanted to talk about that. He's saying if such a solution exhibits motion, we will have broken time translation symmetry spontaneously.
Yeah, now that's a key word that you keep saying that's really interesting too, because I actually did not illuminate myself on this aspect. The word spontaneous.
Yeah.
It's like, is it spontaneous when you're shining a laser on it?
It's
so
not.
I'm a little bit confused at what they mean by spontaneous in this case. Did you illuminate yourself on this?
Yeah, because what they mean, okay, so spontaneous is another word for natural, like in the context of like when we're talking about crystals like salt, like NaCl, like sodium and chloride. When you mix them together, they will spontaneously, meaning naturally, kind of form into its lowest energy state.
So you're not forcing it to become a crystal, is what you're saying. I like that.
Yeah.
Because like when you're mixing NaCl, they will form the crystal.
Yeah.
You don't have to use a scanning electron microscope to make the crystal arrangement. So there is a spontaneity to that formation.
Exactly, yeah.
Gotcha.
There's like a natural ground state formation that happens that's energetically favorable.
Okay, that makes sense.
And it reaches a ground state from that, how would you say? From the interaction.
Those natural interactions.
Yeah, exactly. Right. Yeah. And that's a good way that I saw like spontaneous, but you're so right about like in the lab though, the way the experimentalists are recreating these these events, they're not necessarily
spontaneous events.
I mean, they're not spontaneous. You're driving.
This is really the annoying thing about these words and these things in physics, right? Is you have to like sort the meaning of these things because it's not always the same as a colloquial meaning.
Editor's note once more, just in case the boys have not emphasized enough what makes a time crystal distinct from other many-body phenomena, like the A.C. Josephson effect, can be seen in the following table from the paper Time Crystals in Periodically Driven Systems published in Physics Today. Tiles are said to have many-body interactions that establish coherent long-range order in both space and time. Order renders the system stable against small perturbations that respect the discrete time translation symmetry of an ideal perfectly periodic drive. Crystals exhibit so-called crypto-equilibrium cool branding. Require a sustaining external flux and don't generate entropy.
Yeah, we're using, like Terence is saying, like frequency drivers or something, pumping and kicking the system off so that it can produce periodic motion or whatever in this case. And I want to continue on because the author is saying if the dynamical variable is an angular variable, then the motion will be periodic in time, and the time translation symmetry is not entirely lost but only reduced to a discrete subgroup. Spatial periodicity is associated with formation of ordinary crystals, so it's natural to suggest the formation of time crystals. And mathematically, they play around with these potential energy parameters in the paper, and they reach ones with the lowest energy state is a spatial crystal, and basically they work to find the ones that break spatial translation symmetry. They try to find time-varying solutions to this Hamiltonian.
Yeah.
So they go from spatial derivatives to time derivatives, and they're trying to find all these solutions in the paper. They provide a number of them in cases where you might have these sort of time crystal potentials.
It's kind of like a brute force method.
Yeah. And but the thing is, they weren't verified numerically, and this is why in 2012 when the paper came out, people were like, okay, well, that's intriguing. Time crystals, and he came with a.
You mean verified experimentally or numerically?
No, well, authors were working to verify it numerically, and some people.
What does it mean to verify numerically?
Like run simulations, like build the Hamiltonian, and then like run the calculations and see if they fit the theoretical picture or the framework that the author proposed. But more intriguing, there were experimentalists that looked at the paper and were like, "We're going to try this shit out." I mean, because like the author gave an example of in the second paper a quantum time crystal, or how to like in theory make a quantum time crystal. And like we were saying, it's has to do with many-body localization. And if you look at the Hamiltonian, it's got like the Hamiltonian with the spin interaction stuff. Yeah.
So it sucks.
It's ugly. It's ugly. But yeah, the symmetry, he says, symmetry and its spontaneous breaking is a central theme in modern physics. Perhaps no symmetry is more fundamental than time translation symmetry, since time translation underlies both reproducibility of experience and, within the standard dynamical frameworks, the conservation of energy. Now, this statement it's not obvious, right? Because time translation symmetry, that comes from, and the connection of conservation of energy comes from Nether's theorem.
Yeah.
Right?
Or at least it was very very formalized with Nether's theorem.
That's true. Yeah, that's probably a better way to put it.
Yeah.
I guess
she
like
really tied up a lot of the major concepts together.
Yeah, what's a good way to describe it to like a plumber or something?
Noether's theorem?
Yeah.
I guess that's a good question.
Because it's like you say, oh yeah, I mean because it's not immediately obvious if something is time translationally symmetric.
Yeah. That
energy is conserved, right?
It's not at all. I'm trying to think of how you could even.
Because it's like if you, like, would you? Because I look at conservation of anything, like sort of like if I'm talking to a plumber, I'm like, hey, look at this pipe. Imagine the water flowing through it. There's no pipe. There's no water coming out of this.
Right.
The equations of motion look the same at the beginning and at the end of the pipe.
Right. Yeah. Well, I guess it's just from energy conservation, you could say, because the Lagrangian, let's say, we look at the Lagrangian, right? When you take the derivative with respect to time, I think of the Lagrangian or something like that, right? Then you can see that if it's zero,
you're getting the equations of motion. You're saying?
Then no, if it's zero, then you get See, I don't want to mess up because it's been a while since I've done it.
Sure,
but it has to do something with taking the derivative with respect to time.
Yeah,
the energy, and or the Lagrangian or something. But the Lagrangian is composed of the kinetic and potential energy. T minus V, or kinetic minus potential. So if the energy is not changing, then it's just as simple as saying if energy A is the same as energy B and it hasn't changed with time, then energy is conserved.
Right.
It just happens to be that your Lagrangian is a beautiful little thing that contains both kinetic and potential energy.
Yeah.
Which could be an accident in some sense. I mean, I don't know if it's guaranteed that it had to look like that, but it's a nice way to just to show you that the symmetry is conserved with, or that energy is conserved when you have no derivative of time.
Yeah.
Yeah, I don't know. That's the best.
No, that's a good point. I mean, that's a good point. I would just like stick to the pipe analogy. Like, well, it doesn't really change in time. At every instance in time, things look the same. It's invariant under time. But I don't know if that's a real good physical picture. Maybe not, right?
Yeah, it's hard because when you start doing analogies, sometimes with these really higher abstract things, you completely lose like
the physics.
Well, it's like you're just understanding what the actual physical picture is. You're like, I understand water is conserved, but like you don't know how that fits into the analogy. So sometimes it's better almost to not do analogies for some things.
I see. Okay.
And I feel like that sometimes happens when you're talking about highly abstract concepts, like quantum mechanics. It's kind of stupid to do analogies because you're like, where does the analogy fit into the abstract picture? You don't know you don't know what it is.
Yeah.
Anyway.
Anyways, he kind of keeps going here. In his paper, he hints that the very concept of a ground state or a stable equilibrium state implies a state of the lowest energy has some sort of motion. and is close to fitting the definition of a perpetual motion machine, which I found was like kind of like a hot take to say.
Right.
He's like, I mean, the ground state is kind of a perpetual motion, isn't it?
Yeah, you would think of it like that, but I think the key characteristic they were saying is that a perpetual motion machine, you should be able to extract energy from it indefinitely. And with this system, you cannot extract energy from it indefinitely. And this also has to do with the second law of thermodynamics as well, which I mentioned earlier, is the fact that...
This is a perfect segue to this.
Yeah, so the second law of thermodynamics has to say that basically all entropy always is increasing, or at least staying the same. Your entropy either goes up or stays the same, nothing else. And that's basically saying that all systems will move towards this order. And the reason that this one doesn't break the second law of thermodynamics or laws of conservation of energy is because the energy is not being dissipated. Energy is not being added or removed, so it basically is always the same. It's the ground state continuously, right? The ground state energy is not changing, so it's not violating any energy laws. And then the second law of thermodynamics, it's not tending towards equilibrium or increasing entropy, because once again it's this locked in state of it's an oscillating system, so it's actually the entropy is staying the same.
Yeah, it's persistent equilibrium.
And you can even think of it as like the entropy of, like, let's just say like of a stationary particle. That entropy is not increasing. That's just staying the same. So your entropy can either not change or it increases. One of the two. It's not going to get lower though. So it's not actually breaking any of the fundamental laws of thermodynamics or energy.
Yeah. Yeah, no, I liked it.
It feels okay in explanation. I think we can maybe have more elucidating thoughts on it, but I think that's as simple as you can go, probably.
Yeah. Well, I wanted to kind of go to the paper that, in this quantum time crystal paper, he kind of hinted at what Google made. Because he had like 5 comments at the very end. And he said, and I paraphrase, a more elaborate quantum mechanical system whose states could be interpreted as a collection of qubits might be engineered to traverse in its ground state configuration to a program landscape of structured states in Hilbert space over time.
Oof.
Yeah. In essence,
it's a lot to chew.
So yeah, I tried to dissect what he was saying, and I think in essence what he was trying to say is you could create a crystal where you have your initial state, you shine a laser at it, at the energy that the system requires, and the atoms begin to cascade into its allowed state spontaneously. So it oscillates. The atoms begin to oscillate into other states spontaneously without absorbing additional energy from the initial energy given.
Okay.
Is that a good way you think?
Yeah.
Yeah. Like you shine the laser at it, and it's just the system oscillates. It's like a harmonic oscillator, but like just kicking it and then just watching the harmonic oscillator just go.
Right.
Yeah.
The thing is, I want to know how the connection. I want to know about the superconductor connection with persistent current, because we've already known about persistent current with superconductors for a while, and people have been mentioning that the time crystal is the first object that has this kind of weird ground state energy that has this motion to it. But I'm like, why not the superconductor? I mean, the superconductor, it's maybe not a ground state energy, but it's at least the stable state that has this current that goes indefinitely. So like, why is that one not considered a special phase of matter?
Yeah, I'm not sure. Because
that's literally electrons moving. They're just moving in a circle, right?
Yeah. That's kind of what Frank was trying to show, because in his picture he's like, we have a ring of particles, quantum particles, and then we drive it with a field, and then he came up with in his solutions he had like solitons, these like quasi particles.
Yeah. And
he was like, oh, these solitons in this picture, guess what? They have a ground state that qualifies as a time crystal. But I think there was like physicists, one of them was Patrick Bruno, at some, I don't know, he's a theoretical particle physicist. He was like, he had his qualms about that little picture that he gave. And I think Frank was like, Frank yielded to a lot of the comments that people were giving about his picture about the particle ring system. So I don't think it qualified as a time crystal, the superconductor. And there were certain technical aspects to that.
I see. So it was a superconductor.
Yeah, in his picture, in his toy model, it was a superconductor.
See, I want to know why the superconductor's not mentioned really as much.
Not qualified?
Yeah, because it's like
doesn't qualify as a time
the
crystal?
persistent current is the only other system I can think that has something like that has some kind of persistent property to it that's that lasts indefinitely.
Yeah.
And it seems like this kind of higher order energy state or something, but it's not. It's just like a ground state.
Because it's not a periodically driven harmonic oscillator, man.
Well, we can model this at a high harmonic oscillator.
You just map the position versus time of the the particle. We'll get a harmonic oscillator out of that.
Yeah, true.
Everything's harmonic oscillator at the end of the day, if it's legit.
Well, fuck it. Any closing thoughts on this?
Time crystals, love them or hate them.
I think I don't like the term time crystals because you can already see how loaded the term is.
I see Bert Kreischer tweeting about how we can go back into time now.
Yes, he actually did this once with some stupid thing with time travel.
Yeah.
And you get laymen who get a hold of these terms, and Deepak Chopra is going to use this in his next book. I can see it already.
Yep.
Yeah, I don't like it.
I don't like it either.
I hate the name.
I like spin glass much better if that's the real first version.
Spin glass is 100%.
You're sure that's the first iteration?
Well, that's how it was experimentally verified in some way, because people were like, "Oh, look, we discovered a spin glass thing, this exotic phase of matter," and then it was retroactively adapted to be like, "Oh, this is actually could be considered a time crystal."
Gotcha. Spin glass is better.
Spin glass is better, yeah.
Sounds more physics legit.
Time crystal.
But yeah, the views on spin glass, not so good.
So we'll give it to you on that one. Well, not Frank. Frank, Frank will give it to you on that one.
Yeah, he invented the name.
Yeah. So, yeah, time crystal seems pretty legit. Man, I wish I could pull up the quote, but I can't remember the quote. Because I read so much stuff on this that
your information's all spread out. Same with me.
Yeah, I thought I took the quote down, but essentially the picture was like what we can do with such a time crystal, because people were extrapolating what does it mean for quantum computing applications?
Right. I guess it's a good way to end. Did you see could you think of any other applications that might have anything to do with time crystals?
Yeah, I hinted at how quantum computers essentially would have a RAM, and that's kind of one way you could build the time crystals to do it.
I saw another one where people were saying potentially atomic clocks.
Weird. Well, I'm saying the reason why you could have RAM is because the quantum system is in equilibrium. It's in a stable state throughout. It's not going to be easily perturbed.
Right,
because it's in its lowest ground state.
So you're saying it can store information.
Yeah.
Okay.
And it's very strange.
And the only thing I'm also confused is even though you have this persistent state, how can you store anything when you're not allowed to really manipulate it? Or else if you're manipulating it, then you're dissipating energy.
Well, I think it's robust enough to imagine if you have an array of lattices of these time crystals. Then,
I guess you could just maintain the state, right?
Yeah.
And then whenever you want to dissipate the energy, it doesn't really matter, because then you're just reading out whatever the values are. Okay.
Because I imagine, it would be hard copying the state, but you can write the state.
Well, no, you should be able to copy it as well, because then you can just flip the bits or something individually.
Oh, true. You could have a neighboring lattice, and then that could
or something.
Correct, because it's binary, so then you could copy it.
Sure, I think you could do it.
Yeah.
Okay.
So maybe there's something to this.
You see any other applications?
Well, this is kind of a good example of spintronics, because all of this is just spin.
Yeah, I have a feeling that the spintronics guys might have a new kind of.
They might come back. They might make their comeback.
Yeah, they got a new glimmer in their eye now, maybe, because
I think as far as I could tell, spintronics industry seems like it was kind of in a dead. I don't know. I want to say dead, but it seems like it was in a downturn. Because people were always trying to do the spin wave stuff. By instead of using current to send signals, they want to use the magnetic moments to do a spin wave to send signals, and things along those lines. Of course, we have spintronic stuff in our phones, like giant magnetoresistance, spin valves, these kind of things. But it seemed like it was a little bit stagnant because I think one of the holy grails was a spin wave. Because if you imagine, if you can send communications with spin waves instead of current, then there's potential application of less energy use. And
for sure,
it's like you can have these weird
the
abilities to do things without using electricity.
Yeah, you'd have really low energy
right
usage,
and that could also be things like you can have like less. You wouldn't be shocked. You wouldn't get shocked by components and whatnot.
Well, it's more efficient power-wise and energy cost-wise too. I mean, if you're a smartphone manufacturer, you're looking at this and like with a little twinkle in your eye because you're like
dollar signs in your eye.
Yeah. Because you're like, okay, because battery technology isn't getting any better. So
right. So let's just make things less energy costly.
Yeah,
exactly.
So it's beautiful.
So maybe these time crystals will inspire some spintronics people to make some new cool shit that's just like beyond our even wildest dreams. I don't know. I don't know though. I don't know. I'd have to see. We're not actively in the physics spintronics condensed matter space anymore. We're outcast now, so I don't really get to see the excitement of the field anymore. I don't get to see what people are all riled up about. But I would imagine the condensed matter people are really interested in this.
Well, when I was coming into grad school, it was around the time that the spin glass was was being published, like 2016, 2015.
Yeah.
And I remember in my group specifically, people were like, "Oh, well." One of the students that I was working with was like, "Yeah, the spin glass stuff is just crazy." And I was just like, "Okay." I mean,
I wasn't that amped about it. I remember hearing about it for sure, but
it was a hot topic.
Whatever.
And it died down towards the end because, especially, we're coming to know more like the sort of topology is a huge topic, like topological effects, which are essentially just like basically like the electronic landscape of the part or what the particle sees in its sort of energy space,
material it's in.
Yeah.
Okay.
What the band energy looks like or whatever.
Oh, so it's more of an abstract topology.
Yeah.
Okay.
Yeah. Okay. It's like how the electronic states map in moment, or what the electron sees in momentum space.
Gotcha.
So that's much more abstract.
Yeah, but I wonder if it has. I mean, there are interesting ties here about how it ties into localization, and then you have weird exotic states of matter, and it's just very interesting stuff.
Yeah, this is a cool one.
Yeah.
I feel like condensed matter people have a lot of stuff to play with, and now this time crystal has just added one more, one more thing to the bag of goodies.
Yeah, this is an exciting time to be working on quantum computer stuff, I think, too.
Yeah.
So,
and it's actually a nice little linkage between spintronics and quantum computing. The reason I went into spintronics was because I thought it was much more closer to reality than quantum computing. Because those were the two fields basically that I wanted to choose between in the beginning undergraduate. I was like, I like spintronics, but quantum computing is just real sexy physics. It's got the all the badass videos on YouTube, and it's it just seems like the wave of the future, right? Shor's algorithm, cracking the RSA encryption. But then I was like, you know what? People don't really even know if quantum computing is a real thing or not. And I could be wasting all this time doing quantum research and then nothing panning out. Of course, it's a little naive because any research you do is going to be useful at some level. But I was like, you know what? I want to go spintronics because that one just seems like this real feasible area. It seems badass. It's like I could definitely see the next step in communicating signals as spin waves, versus versus current. So I went down that road. But now it's like these time crystals have given a nice little bridge between spintronics research and quantum computing research, which I don't know if that existed beforehand.
No, I don't think so.
Because now they actually have application in trying to figure out the coherence times with this. So it's interesting.
Very interesting stuff. Yeah.
So you know, people who only went spintronics to avoid quantum computing, now they can have their cake and eat it too, you know?
Yeah, it's good stuff.
So everybody wins.
Yeah, did you have any, like, I mean, I think maybe you think that surmises, like, what your feelings are about
My
the
take on-
applications, yeah?
Yeah. I mean, couldn't really think of anything more clever than that. I think if you're, you know, we're on the outside of the research, so I don't know how good I can do. You know, future predicting is already hard as fuck, right?
Yeah.
The amount of people that get shit wrong when they're projecting into the
Speculate.
future is like a lot.
Yeah.
And I feel like that just gets harder the more removed you are from a subject. So I think that's probably the extent of what I can, you know, speak about.
Yeah. But if we're discovering these, like, new states of matter, I think, showing that we're headed into unknown territory,
Yeah.
which is good.
Yeah.
Which is good for physics.
Which is always good, right?
Yeah.
We like unknown territory.
Yeah.
When things are too well known is when physicists get depressed.
But with that, you know, I think, yeah, leave a comment. What do you think? Do you like time crystals or spin glass better? Yeah.
Right.
Yeah, what do you like? Or,
right.
you know, what are the potential applications? Like, maybe you Googled this stuff and you're like, hey, maybe
Yeah.
let us know. Drop it in the comments. We'll pin the good ones.
Indeed.
Yeah.
All right, folks. So with that said, like, share, comment, subscribe if you haven't already. You know, check us out on Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then patrons, thank you guys so much. We can't do it without you. You know, if you guys want to help support our channel, patreon.com/Eigenbros. Me and Juan do a 30-minute podcast on random crap. So check that out. And we have the Discord as well open to you guys who join the Patreon. And I think that's it.
That's it. We'll see you next week.
All right, guys. Ta-ta.
Bye.